welcome to the last video for curve sketching possible graphs. Only one of these is in your notes, this is all typed in your notes already. All right, so I'm just going to go through, explain it. We'll do the graph together, and then the two that aren't in your notes, I left all the info up, and we can just kind of go over it together. Excuse me. All right, so here what we're doing is we're graphing f of x equals 2x minus 5 to the 1/3 plus 1. That, by the way, is the same as f of x equals the cube root of 2x minus 5 and then all plus 1. A lot of times that plus 1 is put first when you write the radical, so it doesn't look like the plus 1 is under the radical. Although, why would you have minus 5 and plus 1 under the same radical? All right, so first of all, the x and y intercepts. To find the x-intercept, you replace f of x with a 0. Right? So we would subtract 1 from both sides. We want to get rid of that cube root, that exponent of 1/3. So you cube both sides. Actually, I'm going to give you a little arrow here so you know where we're looking at. And you already have this in your notes. So if you cube both sides, right, when you raise power to a power, you multiply exponents. If you remember, hopefully you remember that from algebra 2. Right, -1 cubed is still -1, and 2x minus 5 to the 1. Whoops, no, I just want to get rid of that box. To the 1. Well, okay, new arrow apparently. I doesn't like my drawn arrow. To the 1/3 power, all raised to the 3rd power. You would multiply exponents, so that just ends up being 2x minus 5, as you see over here with my brand new arrow apparently. All right, so now that's an easy solve. You add 5 to both sides, you divide by 2. X equals 2 is the x-intercept. Right, and then to find the y-intercept, you just plug in 0. And it is not that pretty of a number. It is approximately 0.1 to find the y-intercept because you got the cube root of -5. So not all that pretty. And I can't graph cube root of -5, so I need to change that to a decimal equivalent. Vertical and horizontal asymptotes, if any, there's none. This is a cube root. There's none. Domain, cube root, all real numbers. Range, all real numbers. That's true for any odd root. And also true, f of x is going as, this is odd. The leading coefficient technically is a 1, right? It would be the leading coefficient in front of that radical, which is a 1. That's a positive number. So f of x approaches -infinity as x approaches -infinity, and f of x approaches +infinity as x approaches +infinity. That's straight out of algebra 2. All right, so now, not algebra 2. Determine first and second derivatives of the function, all right, and then we'll find the critical points. All right, so the first derivative, whoops, come on over here, arrow. We're talking over here now. Well, there it goes. The first derivative, use power rule there. So the 1/3 moves in front. Reduce the exponent by 1. That arrow's not going to move over here. And then you multiply by the derivative of the inside. This is a chain rule. So you've got the derivative of the inside. The derivative of 2x minus 5 is 2. Right? You can multiply the 2 and the 1/3 together. So 2/3 times 2x minus 5 to the -2/3 power. We should simplify that when we want to find where the first derivative is 0. All right, so now the 3's in the denominator, everything, the 2x minus 5 to the -2/3 power, that all goes to the denominator. Now a fraction equals 0 when the numerator equals 0. But the numerator equals 2, and 2 does not equal 0. So first derivative never equals 0. So there goes that one. However, we still do have a critical point. The critical point is where the first derivative is undefined. Right? And so it's going to be where 2x minus 5 equals 0, and that would be 5/2. So we have one critical point at 5/2. Let's find the second derivative. We need to go back to the negative exponent there. Looks like I had a little bit of a typing issue that I fixed. All right, so gonna, again, power rule. So we'll have 2/3 times -2/3, reduce the exponent by 1 and multiply by the inside part. So that would be, we have a -2 times a 2 times a 2. That'd be negative 8/9 times 2x minus 5 to the negative 5/3 power. Again, simplify that negative exponent, and we've got the second derivative is negative 8 over 9 times 2x minus 5 to the 5/3 power. And again, negative 8 never equals 0. So you set the denominator equal to 0 because that would be your critical point, and lo and behold, it's 5/2 again. So we have both the first and the second derivative are undefined when x equals 5/2. All right, so at the bottom there it tells you since the first derivative is never 0, the only critical value is where the first derivative does not exist. So we found our critical points. Let's continue on. Do some interpreting. Complete a sign analysis of the first derivative to determine where the intervals where the function is increasing and or decreasing. All right, so our only critical point is 5/2. If we plug in something less than 5/2 like 1, we will be increasing, right? Because if I plug in 1, I have it's going to end up being a positive number when we plug that into the first derivative. If we plug in something greater than 5/2, we still get a positive number. So increasing everywhere, negative infinity to infinity. So 5/2 is not a relative extrema. Right? There are no relative extrema since there's no change in sign in the first derivative. No matter what, it's increasing. How about the second derivative? Maybe we have an inflection point. All right, so second derivative, you plug in something less than 5/2, positive. You plug in something, because we have a negative and a negative, right? If you plug in something greater than 5/2, it is negative because the denominator will be positive while the numerator is negative, right? So we have a change in concavity. That means that 5/2 is going to be an inflection point, right? Because f double prime of x changes from positive to negative at 5/2. So we do have an inflection point. Graph is concave up from negative infinity to 5/2 because second derivative is positive. And actually, let's put that in. I don't know if did I put that in there? Let's add that in there. And add that to your notes, the f double prime of x is greater than 0 when x is less than 5/2, and concave down from 5/2 to infinity because f double prime of x is less than 0 when x is greater than 5/2. All right, let's just make sure we're clear here. We look for inflection points concavity by saying the second derivative equal to 0 and completing a sign analysis of the second derivative, which is what we did. Because the second derivative is positive for x less than 5/2 and negative for x greater than 5/2, 5/2 is an inflection point, right? And that's for f of x. So one critical point, 5/2 for f of x, which was an inflection point. All right, so let's draw our graph. All right, so here we have a little chart. Sometimes that's helpful, all right, because you've got everything summarized in one spot, because now this isn't just a possible graph, this is the graph. All right, so when x is 2, y is 0. Right, so we do have an x-intercept. Let's graph that point. We have a y-intercept. It's approximately negative 0.71. So, that's about 3/4. There we go. We have, so 5/2, the first derivative did not exist. The second derivative did not exist. This is the y value for f of x, all right? So you can just plug that into the original function. If you plug in 5/2, right, you're going to get 0. The cube root is 0 plus 1, so that would be 1, all right? So we do have a point 5/2, 1 right here. That is an inflection point. So we've got to try to change concavity there. Then we have one other point we plugged in there so we can have some points on either side so we can get that concavity right. If I plug in a point greater than 5/2, such as 3, right, well, we have if we plug that into f of x, we get 2. So that is another point for us to try to get the concavity correct, right? So let's take a look at what's happening. So at 2, 0, the function is rising, right? Because, so y prime here, that's our first derivative. Here's a second derivative. First derivative's positive, second derivative's positive, rising, concave up, all right? And then we get to 0, negative 0.71, so that's actually the lowest value. All right, so here's our lowest value. 0, negative, that we have on our little chart here. 0, negative 0.71. First derivative is positive. Second derivative was positive. All right, so that is a y-intercept, rising, concave up. Right, at 2, still rise, 2, 0, still rising, concave up, no changes there. At 5/2, we get to an inflection point. We change concavity. After that, still rising, because that first derivative is still positive. First derivative is positive everywhere, right? But the second derivative is negative, so we're concave down. All right? And this is a cube root, so you should have in your mind what a cube root looks like. But now let's graph that, and hopefully I can get my inflection point looking like an inflection point. So I'm just going to, just as a reminder, this is kind of what the graph should, no, that's a horrible looking graph. So cube root kind of looks like that. All right, so we should kind of have that in our minds. Here's the concave up part. Here's the concave down part. And here's the inflection point. All right, so this is in general what a cube root looks like. Let's try to get ours in the right spot. All right, so concave up, rising, rising, change, concave down. Whoops, a little too down. It's supposed to be still rising. Still rising, but concave down. There we go, that looks pretty good. All right, so right here, where it's in green, that's the inflection point, right? And that was at 5/2, 1. All right, and then concave up. Concave down. I was going to put C down because I don't have that much space there. And there were no extrema values. So that was it. Okay. So we're done with this graph. Okay. It looks pretty good. All right, so I looked and I didn't see these in your notes. If I'm wrong, if I remember to add them, then here you go. But I'm not going to erase it because I don't think I'm not sure if it's in your notes. All right, but let's take a look at the information at the top, all right, and then we'll look at the explanation at the bottom, explaining everything. All right, so a continuous function, h of x, is described in the table below. Use the information to complete exercises 55 to 58. All right, so this is all about this graph here. All right, so it gives us some selected values of, tells us some things about h of x. All right, so we have some points, and I graphed those points. So we have the point -4, -5, -2, -4, -1, -2, 0, 1. All right, those are just points on the graph. All right, I literally just graphed the points, and we knew it had to be continuous, and we connected those points. All right, no big deal. All right, and then we have the points 1, -1, 3, -2, and I lose my ability to hit the point. There we go. And 5, 0. So these are just points from the graph. And I don't know what happens after that, so the graph just stops. All right, so it says increasing and concave up from -4 to 0. All right, so if you look, the graph from -4 to 0, increasing, the y values are getting larger, and it is concave up. Decreasing and concave up from 0 to 3, we manage that, and then increasing and concave up from 3 to 5. So notice there's no change, we just keep being concave up. All right, so h prime of x is greater than 0, where f of x is increasing, h prime of x is greater than 0 on -4 to 0, and from 3 to 5. That's where the graph is increasing. So we're just evaluating some things about our derivative here. And actually, I'm sorry, that's question 58. So why don't I do them in order? So there's our graph. And then 56, estimate the values of h prime of -2, h prime of 1. Do these values support the claim that h of x is increasing on the interval -4 to 0? Give a reason for your answer. Right, so h prime of -2 is, now, how did I get these values? These were, I estimated. All right, so these are estimating based on the graph. So these were estimating from the graph. Hence the reason for the little lines everywhere. All right. So we look at this. And what are we estimating from the graph? We're estimating the slope. Let me make sure that's clear to you. So we're estimating the slope of h of x from the graph. All right. So at -2, the slope appears to be 1. If f prime of x is greater than 0, f of x is increasing, right? 1 is greater than 0, so it's increasing. That matches what it says there, because it says -4 to 0, increasing and concave up. H prime of 1, -3 halves, right? So if f prime of x is less than 0, f of x is decreasing. Notice it says from 0 to 3, decreasing, so that matches. And how we got those values was estimating the slope of h of x from the graph. Determine the x values at which h of x is not differentiable. Give a reason for h of x not being differentiable at those values. So notice that nice little pretty cusp. F of x is not differentiable at x equals 0 because there's a cusp at x equals 0. And we know corners, cusps, vertical tangents, not differentiable. And then I could not squeeze the answer to 58 on the graph. On what intervals of x is h prime of x greater than 0? Give a reason for your answer. So h prime of x is greater than 0, where f of x is increasing. All right, so h prime of x has to be greater than 0 on -4 to 0 and 3 to 5. You should be able to tell me where a graph, where h prime of x is positive or negative based on whether the graph of the original function is increasing or decreasing. I don't know that they asked us, but I gave it to you anyway. H double prime of x is greater than 0 on -4 to 0 and 0 to 5 because h of x is concave up. All right, so right here, concave up, concave up. Since h prime of x does not change signs, there's no inflection points. So there are no inflection points. There is a relative max. All right, so there's a relative max. Let's add that. They didn't ask us that, but it's okay. There's a relative max at x equals 1. Specifically, that was, excuse me, x equals 0. X equals 0. X equals 0. X equals 0, specifically 0, 1. Right? So that, and that first derivative is not 0, but the first derivative is undefined. I should put a 1 in there. Or 0, excuse me, 0. Our first derivative at 0 is undefined, right? It does not exist. Or I could put that backwards, e, and put it, right? The line through it, that also means does not exist. Right, so the first derivative does not exist at 0, but that is a relative max, right? And it is a relative max because f prime of x changes sign from negative to positive, right, at x equals 0. Right? So that is a relative max. It is not an inflection point. There is no change in sign in the second derivative. Right? And it doesn't exist for the second derivative either. All right, so here is just interpreting from the graph. You should be able to interpret increasing and decreasing you should be able to interpret increasing and decreasing if I give you the derivative. You should be able to determine concave up, concave down if I give you the second derivative. And you should be able to interpret where the first derivative and the second derivative are positive or negative based on the graph. Here's the second one. I guess I wanted to do 46 through 48 after I did 50. A function f is continuous on the domain negative 2, 4. Additionally, f of negative 2 equals 5, f of 4 equals 1, with the first and second derivatives having the properties shown in the graph. Use the information to answer the question. So we didn't do a graph, we just answered the questions. At what value of x does f have a relative extrema? Classify the extrema by type and give a reason for your answer. All right, so look at our first derivative. We go from positive to negative. That means there's a relative max, right? So f of x has a relative maximum at x equals 0 because f prime of x changes sign from positive to negative at x equals 0, right? It's right here, right? Positive to negative, relative max. Oops, there goes my eraser. At what values of x does f have a point of inflection? Now we're looking at the second derivative, right? Notice, not here, not at 0, no change in sign, positive, positive, concave up, no inflection point. However, at x equals 2, right, the second derivative goes from positive, concave up, to, let's see if I can do that, negative, concave down. We have an inflection point at x equals 2. All right, so you should be able to interpret where there are inflection points just given the sign of the first and second derivatives. You should be able to find maxes and mins and inflection points. All right, so f of x has a point of inflection at x equals 2. I can also call that just f, because f double prime of x changes sign from positive to negative at x equals 2. On what intervals is the graph of f increasing, decreasing, concave up, or concave down? Justify your reasoning. All right, so where the first derivative is positive, the graph is increasing. So f is increasing on negative 2 to 0 because f prime of x is greater than 0 on negative 2 to 0. That is a perfectly good answer as to why it is increasing, right? Right to the point. F is decreasing on 0 to 2 and 2 to 4 because the first derivative is less than 0 on that interval, right? F is concave up from negative 2 to 0 and 0 to 2. Make sure you do not write that as negative 2 to 2, all right? The second derivative does not, and the same thing with the first derivative. The first derivative and second derivative do not exist at 0. Do not make that interval include 0, all right? So make sure you break up the graph at 0, all right? So especially on that second derivative, because there's no sign change, right? So it's not really a big issue on the first derivative because it changes from increasing to decreasing at 0. But likewise, on the first derivative at 2, notice decreasing and decreasing. You want to, but the first derivative is 0 at x equals 2. Make sure you break that interval up at 2. Don't make that interval from 0 to 4, okay? So that's why we have 0 to 2 and 2 to 4. So f is decreasing on 0 to 2 and 2 to 4 because f prime of x is less than 0 on the interval. F is concave up from negative 2 to 0 and 0 to 2. Notice I broke it at 0, right, because the second derivative does not exist at 0. So do not say negative 2 to 2. right? Because the second derivative is greater than 0 on the interval. And I don't know about you, but I can't read that bottom part. F is concave down from 2 to 4 because the second derivative is less than 0 on 2 to 4. All right? So there we have interpreted from the table. I absolutely expect you to be able to interpret from a table. And if you have trouble, then you ask me. And I help you. Oh, and then I'm going to stop here. I think this might be somewhere else in the notes, but this is something we've done before, and we may even have that in the notes. But I may want to go over it as a review, but I'm going to not go over that right now because that has nothing to do with curve sketching. But that is the end of my video here. Thanks for watching. In the last series of videos for curve sketching, we're going to be comparing the first derivative, the second derivative, and the original function. And what does each graph tell us about the other graphs? All right, and so at this point, you may do the curve sketching homework too. I do not think I'll be doing a video just for that. I think you can join me in office hours for some help. But at this point, you can do the homework. And then after the next series of graphs, you can do the little worksheet, although you can do a lot of that little worksheet where you're reading explaining the first derivative and second derivative from the graph and so on. Right? So you're telling about the others based on a graph of one of them. Right? So you should be able to interpret this. If I give you the graph like we did over here, you should be able to tell me about the first and second derivative. If I give you the graph of the first derivative, you should be able to tell me about the original function and the second derivative. If I give you a graph about the second derivative, you should be able to tell me about the original function and the first derivative. All right? So, and in other words, in terms of where is it concave up, where is it increasing, and so forth. Right? So that's all I have for this video. Bye for now. Thanks for watching.